Okay, so last lesson you were introduced to the concept of circular motion. And one of the last things that we were looking at is that there will be one acceleration always pointing towards the center of this movement. Right? So let's say that this is our circular motion, part of it. So there is some particle which is moving that way, but it's been tilted, and then when it reaches a new position now, it's moving that way, right? So let's call this our old velocity. Could be 0 and new one, okay? Our new velocity. Or we could just do as we have been doing before. Let's call this u and this v. That's better. Right? If this is the center of our motion, it has went through an angle of theta. Right? So this angle here would be theta. Please don't worry about if it's 90, if it's not, because what we're going to do here, we want to find what is the change in velocity. Because if you remember, acceleration is the rate of change in velocity over time. But now we have vectors. So when we want to work with those vectors, if we want to do change of velocity, so let's say that this is change of velocity, it would be final velocity minus the initial one. But if those are vectors, we cannot just subtract those values. So we would have to work with a vector. So this is vector u, and this is vector v. If I'm trying to do v minus u, I can take my negative u. This is negative u, my vector negative u, which is what is important to me. And I can actually just move it around. So I want to add v and negative u. So I will walk in direction v and then in direction negative u. Okay, so let's just rearrange a few things. So this is my v, this is negative u, so my sum would be this vector, delta v. If you notice, it would be the vector pointing to the center of our circular motion. Alright, so far so good. So delta v, in this case, the vector would be this, this sum. Now, as we have defined before, this angle was theta. So the angle between those vectors is theta. So let's take a look at this triangle. Let's make it a bit larger. Okay, now remember that this theta, we don't know if it's 90. If we took another velocity here, you would make a different triangle. That angle would not be 90. Seems like 90 here, but it might not be. It might be any angle. So for us to calculate anything here, we could split this angle in half. So we would have theta over 2 here and theta over 2, or delta theta, okay, because it's changing angle. And now we've got a right angle here, right? So this is going to be delta v over 2, because we have split this in 2, delta v over 2. This is not the angle itself, but it's the magnitude. So this length here is delta v over 2. This length is delta v over 2. This length is the length of u. And this length is the length of v. So if we look at this triangle here, we can find some relation between this angle theta over 2, or delta theta over 2. Let's call it delta theta. Okay, delta theta. So delta theta over 2. What relation can we find? Well, this is the hypotenuse, and this is the opposite side. So hypotenuse and opposite sine, it's so, right? So katoa, so sine opposite over hypotenuse. So sine of delta theta over 2 will be our hypotenuse, which is u, over so katoa, so opposite, so delta v over 2 divided by u. Or if we rearrange those, we could simply get this u to the other side, right? So we would have u sine of delta theta over 2 is delta v over 2. This is an important relation, right? Because we are basically relating the change in the vector with its magnitude and the sine of the angle that we have displaced. Now, since the acceleration is the change in velocity over change in time, now we can use what we have found here, because we know that delta v, the change in velocity, would be 2u sine, right? So this is, so getting the result that we found here, it's 2u sine of delta theta over 2 over change in time, right? Now, to get rid of this time, let's make another relation here. If you remember, our speed was distance, displacement over time. So here's just change of displacement. If I don't start counting at 0, if I start counting at some point, then I have change in displacement. So change in displacement, we know something regarding change of displacement when we have circular motion. So we should remember that this is r delta theta, and this is just the same. So we can actually rearrange those things and get some kind of relation, which is delta t, so the change in time would be r delta theta over v, just by rearranging those values, right? Those variables. So we can now use this into here. So if we put those numbers in, we would have 2u sine of delta theta over 2 over delta t, which is r delta theta over v. Now, something important to notice is that this magnitude doesn't change. So the magnitude of this vector and the magnitude of this vector is the same. So v and u, the values here, their magnitudes, so they're the same. So I can actually just replace v for u or u as v, doesn't matter. So we can rearrange those things. So we can combine those two. So u, 2u squared, I've chosen u, could be v, sin of delta theta over 2 over r delta theta. Now, I will just multiply this and divide by 2. So I have delta theta over 2 down here as well. I don't know if it's clear to see. There we go. Hope it's better now. So I'm keeping delta over 2, delta theta over 2 here, and delta theta over 2 because there is a reasoning that we can make here, which is if our angle is very, very small, remember that we're using this angle, we're measuring it in radians. So if this angle is very, very small, the sine of the angle is very, very similar to the angle itself. So we could approximate this as, and I'll get rid of those 2's. So I would have u squared over r delta theta over 2 over delta theta over 2, and we can cancel those out. And then we get to our centripetal acceleration, which is velocity squared over the radius. Well, use whatever r you want. And that's in your booklet, and that's the most important, that's one of the most important equations in this chapter. Now, important to notice though that this is a vector and it's going to follow the direction which is pointing inwards. So here the acceleration would be here. Here it would be pointing that way, right? If I had another point here, it would be always pointing towards the center of the motion. The center of the motion, the center of your trajectory, your circular motion. And now that we have the centripetal acceleration, we can just get the force. So the centripetal force, if you remember your Newton's second law, force is mass times acceleration. So it would be mass times u squared over r. So this is your centripetal force. So a very simple application. Let's say that we have a car. I'm looking from the top view. Okay, so this is my car. It's going in a circular path, right? So it's going to follow this path here. And basically we're going to analyze how can we calculate our velocity so that car doesn't skid, so it doesn't like lose its friction with the track, right? So there will be some centripetal acceleration pointing inwards, and what is going to produce that acceleration is the friction of the tires with the floor. So if you look at the car, if you look sideways, we could make a free body diagram with the forces. I'll not make a free body diagram, I'll just draw the forces here. So we would have the weight, which is pointing downwards, and it's mass times gravity. And we would also have the force of friction, which is pointing inwards. And that's our centripetal force as well. I call it Fc. And we know that this is m v squared over r. This v squared over r, or u squared over r, is what we saw on the previous slide, and it should be in your booklet. Okay? So how can we calculate the velocity so it doesn't skid? Well, for it not to skid, the sum of the forces would have to be zero. Right? The sum of the horizontal forces, it would have to be zero. So if the sum of the horizontal forces have to be zero, my centripetal force will have to be less than my static friction, right? Because if it's too large, then I'll lose the grasp with the floor. And my static force is the static friction times my normal force. The normal force is the one pointing outside here, upwards, right? Here it would be up, so coming out of the plane of the paper. Here it would be going up, r, right? And that normal force is going to be equal to the weight. So my relation, my equation would be this one. And then we can cross out some things. So we know that now we know that it doesn't, the mass doesn't matter. And if we were looking for speed solely, we would have that our speed would have to be, and then we just rearrange, right? So r will multiply, we'll have gravity as well, and root. So there we go. The radius of the curve, the static friction of the pair, tire, asphalt, and g, which is your acceleration of gravity. So sometimes, in order to avoid skidding, what is done by engineers when they design tracks for bicycles, for cars, for especially racing cars, is banking. So basically, when you're going towards a curve, they bank the curve. So let's say there is a car here, right? I'm looking from the back of the car, for example. So it's trying to turn that way. So this bank, what's going to do, this angle here, some parts of our normal force will also contribute to our centripetal force. So for example, here we would have our friction, right? So our friction is that way, our weight is that way. Oh, this is not going to be exactly that because of the angle, right? So part of our normal force will help increasing our centripetal force. Our centripetal force here will still be mv squared over r, right? But the difference now is that depending on this angle, we'll have more of this static force. I'll call it Ft, just like we're doing mechanics, right? So this static friction will add up with a bit of the normal force, and then it's going to be stronger. So we have more grasp with the floor and a lower chance of skidding. if we make a very simple free body diagram of this situation here, okay, so we would have a force downwards, which is mg. We would have a force upwards, so since it's not moving up or down, this force upwards will also be mg. They will have to cancel out. We will have a normal force, which is this, right? This is going to be the same angle as the banking, right? So if this is n, let's say this is our normal force, this would be n cosine of theta. Okay, we're basically splitting this force, and the normal portion, which is going to help us now in the preventing skidding, is going to be n sine of theta. So we have decomposed this force into two other forces. All right, and that's it. So we'll also have our friction. So friction will be parallel to the floor, so ms and normal. Alright, so with this relation here, right, we can find out, we would also have to, this would also be angle theta, so we would decompose friction as well, and we would have a portion of friction which is helping us towards the center of our movement. So let's solve a simple example now. So a hammer thrower, in an athletics competition swings the hammer on its chain around 7.5 times in 5.2 seconds before releasing it. The hammer describes a circle of radius 4.2 meters and has a mass of 4 kilograms. Assume that the hammer is swung in a horizontal circle and that the chain is horizontal. Calculate for the rotation: 1. The average angular speed of the hammer. 2. The average tension of the chain in the chain. So let's do the first question first, okay? So, well, A1. So we're being asked the average angular speed, right? So angular speed, well, first of all, how many revolutions do we have? So we go around 7.5 times, right? So 7.5 full swings, right? So 7.5 times 2 pi radians. So our full angle would be, this is theta, right? That's our angle. That would be 15 pi. All right? So angular speed is the change in our angle over time. So it's the angular displacement over time. This is our angular displacement. So average angular speed, so theta over time. So that's 15 pi in 5.2 seconds. And that would be around 9.1 radians per second. Now, since our motion is horizontal, and it makes clear that that motion is horizontal, the weight of our object will not have any influence in it. So it's basically the average tension in the chain will be due to the centripetal force that we are exerting to not let this hammer fly away, right? So we're holding to the hammer and we're making a force to keep the hammer moving in a circle, and when this force is released, then the hammer goes away. So the tension would basically be our centripetal force, which is m v squared over r. Now here, if you remember that v equals omega r, right? This is something that we saw last lesson. We can change this into different equations, right? So if we just put those here, we would have m r omega squared. Right, so this is a better, more suited equation since we know the mass, we know the radius, and we know the circular, our angular speed. Right, if we knew our linear speed, then we could use this one. And we can even find the linear speed, but we don't care now. So the mass is 4 kilograms. The radius is 4.2. And our angular velocity, our angular speed, because we're not taking into account the vector, is 9.1 radians per second. So if we multiply those numbers, we would find a force of 1,400 newtons, which is 1.4 kilonewtons. And that would be it. Now, comment on the assumptions made in the question. Right, so we have to comment on the assumptions. So we could, well, first of all, usually if you watch the Olympiads, you'll see that there is an angle that they usually do, like almost 45 degrees with the horizontal. That's to achieve maximum range, right? So, and even if the plane in which the athlete was spinning the hammer, even if it was horizontal, the weight of the hammer would contribute to the system. So there would be a component of the tension to consider this, because the hammer would try to fall a bit, so we will have to spin it a bit faster so it wouldn't fall vertically. But both assumptions are unlikely.